Well, first of all, it is a Big Bang model. In other words, there is a Big Bang, but the Big Bang was not the beginning. The Big Bang theory suggests that the universe emerged out of nothing, signifying the beginning of the universe. Before this, there was nothing, no time, no space. However, what if I told you that time doesn't exist and that the Big Bang theory is incorrect? Recent discoveries made by the James Webb Space Telescope provide evidence that challenges the validity of the Big Bang theory. It turns out that the Big Bang wasn't the beginning of the universe, and, in fact, time itself may not exist. What's interesting is that this idea is supported by the renowned British physicist Roger Penrose. Now you may wonder how the James Webb Space Telescope proves that time doesn't exist and, if the Big Bang theory is flawed, what alternative theories have been proposed to explain the origin and evolution of the universe? Let's delve in to find out. The idea that our universe has been expanding since its beginning over 13.8 billion years ago in a hot and dense state, known as the Big Bang theory, has faced challenges with recent images from the James Webb Space Telescope. While these images are captivating to the layman, they have caused concern among cosmologists and astronomers. The surprise felt by experts stems from the fact that these images contradict the Big Bang theory. This theory has long been upheld as true by many scientists, so the new data has caused a significant upheaval in the scientific community. Astronomers like Alison Kirkpatrick from the University of Kansas are troubled by this development, questioning the validity of their previous work. The issue lies in the characteristics of the galaxies depicted in the JWST images. These galaxies appear unusually small, smooth, and surprisingly old. According to the Big Bang theory, as space expands, galaxies and other objects should appear larger as they move away from us due to the stretching of light. However, the JWST images show that the galaxies become smaller as the distance increases, which contradicts the theory. Even galaxies with greater mass and brightness than our own Milky Way appear 2 to 3 times smaller in the JWST images compared to previous observations by the Hubble Space Telescope. Additionally, the redshifts observed in these galaxies are also 2 to 3 times greater, further challenging the assumptions of an expanding universe in the Big Bang theory. These facts suggest that distant galaxies must be exceptionally tiny to account for this optical illusion, which is implausible. The presence of these small and smooth galaxies undermines the notion of expansion, thus casting doubt on the Big Bang theory. Supporters of the Big Bang theory were aware that their assumptions required the existence of these small and dense galaxies, often referred to as Mighty Mouse galaxies, based on previous observations from the Hubble Space Telescope. However, the JWST images have worsened the situation by refuting the idea that these tiny galaxies could grow into larger galaxies through collisions or expansion. The JWST images show well-formed spiral structures and smooth disks, similar to the galaxies we observe today. This contradicts the expectation of mangled and distorted galaxies resulting from collisions. Without significant mergers, the tiny galaxies cannot become 100 times larger, indicating that they were not initially small. This finding challenges the optical illusion predicted by the expanding universe theory, suggesting that there is no expansion and, consequently, no Big Bang. The age and abundance of galaxies in the JWST images also pose problems for the Big Bang theory. By using infrared filters, the JWST can capture the colors of distant galaxies, allowing astronomers to estimate the age of the stars within them. According to the theory, these far-off galaxies should represent a time around 400 to 500 million years after the Big Bang. However, some of these galaxies show stellar populations that are over 1 billion years old, contradicting the assumption that nothing could have existed before the Big Bang. Moreover, theorists expected that as the JWST peered deeper into space and farther back in time, there would be fewer galaxies and eventually a dark age. However, the images reveal galaxies as large as the Milky Way even just a few 100 million years after the theorized Big Bang. Furthermore, the number of galaxies observed at redshifts above 10 is at least 100,000 times greater than predicted by theorists. It is implausible for so many large galaxies to form in such a short period, challenging the Big Bang theory once again. These findings have led to the questioning of the concept of time itself. Some scientists argue that time is merely a human construct, a way to differentiate between the present and our perception of the past. They propose that time is an illusion created by human memories, suggesting that everything that has ever happened or will ever happen is occurring simultaneously. This perspective challenges the idea that time must move strictly in a forward direction. Some adherents of the Big Crunch theory even suggest that when the universe stops expanding and starts contracting, time may reverse, leading to a reversal of the cooling and expansion observed in the Big Bang. Eventually, the universe would collapse back to the point where it began. The implications of what comes after a Big Crunch remain uncertain, with various theories proposed. Some speculate that the universe may undergo a fresh start with another Big Bang, while others suggest the universe may simply cease to exist. Certain ideas propose a cyclical nature, with a process repeating multiple times, creating multiple universes. This ongoing debate about the direction of time has prompted scientists to question its fundamental nature. Some argue for a block universe concept where space and time are interconnected in what is known as spacetime. According to a theory supported by Albert Einstein's theory of relativity, time and space are part of a four-dimensional structure where each event has its position in spacetime. This implies that everything, including the past and future, coexists in spacetime, making them equally significant alongside the present. Physicist Max Tegmark from the Massachusetts Institute of Technology aims to address this concept. He suggests that reality can be depicted as either a three-dimensional space where events unfold over time or a four-dimensional space where nothing changes. If the latter is true, then it implies that everything already exists at any given moment, encompassing the past, present, and future. However, we have an illusion that the past has occurred and the future is yet to come, leading us to perceive change. Julian Barber, a British physicist who has written extensively about time, offers his perspective on this matter. He describes our experiences as a series of nows and points out that we are only aware of our brain state. Our perception of the past arises from our brain storing memories. Barber refers to the spacetime theory where each point in this conceptual country, which he calls Plutonia, represents a now. He suggests that what we believe is a past is merely an illusion created by our brains. This discussion brings us back to Albert Einstein's theory of spacetime, which has caused some confusion in the field of physics. Scientists are now contemplating what would happen if Einstein's theory were proven incorrect. Would discarding the theory of spacetime help us gain a better understanding of the universe? This would be a significant development. Throughout history, scientific revolutions have been crucial for progress. Dissatisfaction and doubts eventually lead to the emergence of new theories that replace the old ones. This pattern has occurred numerous times in the fields of astronomy and physics. Initially, humanity believed that Earth was at the center of the solar system, a belief that persisted for over a millennium. However, Nicholas Copernicus proposed a different theory, suggesting that it would be simpler to consider Earth as just another planet orbiting the Sun. Despite initial resistance, this heliocentric model gained support with the advent of telescopes. Isaac Newton also contributed to our understanding, explaining that the gravitational force of the Sun causes planets to orbit it. According to Newton, objects with mass exert gravitational attraction on each other, which explains Earth's orbit around the Sun and the Moon's orbit around the Earth. Newton's theory dominated scientific thought for nearly 300 years until Albert Einstein introduced his general theory of relativity in 1915. This new theory successfully accounted for inconsistencies in the orbit of Mercury and was famously confirmed during a solar eclipse observation in 1919 off the coast of Africa. Contrary to Newton's idea of gravity as a pull, Einstein envisioned gravity as a consequence of the curvature of space. He proposed that all objects in the universe exist within a four-dimensional fabric known as spacetime, and massive objects like the Sun curve this fabric, causing planets to follow the curvature in their orbits. To observers, this curvature manifests as a Newtonian gravitational pull. Einstein's theory of spacetime has reigned supreme for over a century, overshadowing competing theories. The discovery of gravitational waves in 2015 further cemented its significance. However, like its predecessors, it may soon face challenges as it clashes with the other prominent theory in physics, quantum theory. The quantum world is known for its peculiarities, where particles can exist in multiple places simultaneously. In the 1930s, Erwin Schrödinger famously illustrated the strange nature of quantum superposition with his Schrödinger's cat thought experiment. It involved a sealed box containing a vial of poison connected to a hammer triggered by a quantum measurement. According to quantum physics, until the measurement is made, the particle exists in a superposition of both states, leading to the paradoxical scenario where the cat is simultaneously alive and dead. However, this picture of quantum superposition cannot be reconciled with a continuous and smooth fabric of spacetime. Even Sabine Hossenfelder, a theoretical physicist at the Frankfurt Institute for Advanced Studies, acknowledges this conflict. According to Einstein's theory of spacetime, a gravitational field cannot be in two places simultaneously. It's influenced by matter and energy and is subject to curvature. However, quantum physics suggests that matter and energy can exist in multiple states simultaneously, defying traditional notions of locality. This raises the question, where does the gravitational field,